All right, good afternoon. So I want to continue talking about induction and going through some examples and looking a little bit at how this relates to code. Any questions before we jump into that? I also want to talk about the homework that I just graded and gave back to you, and answer any questions on the current homework and answer any questions on the midterm that weren't already answered on Monday. So this is your chance for questions.
Yeah, I have a question.
Okay.
So with the current homework, how formal do we need to be in proving that a number is prime or not? Do you need us to write a formal proof, or can we just show that if a number is not divisible by a certain number of primes, then it's therefore prime?
Let me see. I just want to know which ones are primes and which ones are not, and if they're not prime, show me a factor. But you don't have to prove, for example, that 17 is prime. You can just tell me 17 is prime, and figure that out, by doing some trial division or something like that. But I'm not looking for any sort of formal proof here.
Okay, thank you.
Yep. All right, is everybody... Yeah, go ahead.
For number 1 on homework 6.
Okay.
I got that all of them were false because how I know modulos to work is that let's say for the first one, it's 2 mod 8, and 2 is less than 8, which means that there are no multiples that divide into 2, which would make the answer 2 instead of 26.
All right, so yeah, so 26 congruent to 2 mod 8. Is this true or false? So in reality, there are a lot of things that are congruent to 2 modulo 8. If we say that x is congruent to 2, and I'll just assume this is all mod 8. If we say x is congruent to 2, that means x equals 8 times something plus 2 left over. In other words, 8 goes into this some integral number of times with 2 left over, right? So 26, if we try to reduce 26 mod 8, that's actually 3 times 8 plus 2. So the remainder, when you divide 26 by 8, is 2, so that is congruent to 2. It also turns out 10 could be written as 1 times 8 plus 2, so 10 is also congruent to 2. Well, guess what? These two facts would also tell us that 26 is congruent to 10. And there's this one aspect where I said normally when I ask you to tell me what is this congruent to mod 8, I'm looking for a number between 0 and 7. But two things can be congruent to one another, and something can be congruent to something else, even if that thing is not between 0 and 7. That's totally legit. How do we know that 26 is congruent to 10? Because I can write 26 as 2 times 8 plus 10. So 8 goes in an integral number of times with 10 left over. That's enough to say 26 is congruent to 10. So this would be a true congruence, and there's an equivalent expression to say that two things are congruent. We could actually say 26 minus 2 is going to be congruent to 0. In other words, 8 divides the difference of 26 and 2. So all of those homework questions where we want to know, is this congruent to that, can be solved by saying, is the difference between those two numbers a multiple of the moduli?
Okay.
Does that make sense?
Yeah, it does now.
Okay. And yeah, so someone just commented in comments that you can take the first number minus the second, see if that's divisible by the moduli. And that should not depend on the order in which we do these things. 2 minus 26 is negative 24. Well, that's also divisible by 8. So 2 should be congruent to 26. So you can do those in whichever order strikes you. And this helps with the negatives, right? Negative numbers are kind of strange. So for example, 2 would actually be congruent to negative 6 modulo 8. Well, yeah, we can write negative 6 is negative 1 times 8 plus an extra 2 left over. But an easier way to see this is just 2 minus negative 6. That's 2 plus 6, that's 8, that's a multiple of 8. Alright, and then question 2, just tell me which ones are prime, and if it's not prime, show me a number other than 1 in itself that divides it. Question 3, just factor these into products of powers of primes. And there's nothing to prove there. And then question 4 is Euclid's algorithm on those 5 pairs of numbers to find a GCD. And then for your own sake and peace of mind, just confirm that that GCD actually does divide both of those numbers. That's a good sort of sanity check.
So how do we differentiate? Because in homework 5, when we use the modulos, the thing that it was equal to was the remainder. So how do we differentiate between these and the ones on homework 5? Like for example, when we said 2 to the second mod 7, that was equal to 4.
Say that last part again, when we said what, 2 to the second?
Or actually, just for the answer to that one, when we said 2 to the 1/30th power mod 7 was equal to 2.
It's congruent to 2. It's not actually equal to 2. Right? But you can show that 2 to the 1/30th is congruent to 2. And it's exactly the same thing. It's saying if you take this and you subtract 2, that should be a multiple of 7.
Okay. So what you're saying is that there's multiple different things that can be congruent.
Oh yeah, there's an infinite number of things in general that it will be congruent to. Basically, any number that's 2 more than a multiple of 7 is congruent to 2. And so for homework 6, we can just sort of take the difference to see that that's the case. For these questions where we had 2 raised to the 6002, that's a bigger number than we really want to deal with. But we could. So, well, it's not that big. Right, so if you do 2 to the 6002 minus 4, you get that number. If you do that and divide by 7, you get an exact integer. So that's a long-handed way of finding what 2 to the 6002 is congruent to, or confirming that 2 to the 6002 is congruent to 4. But the whole point on the homework, which we'll go through in a minute, was, not having to do that big long calculation, come up with that ginormous number. All right, good. Other questions? All right, is everybody clear on the homework? Sorry, not on the homework, on the midterm. So the midterm is Friday. It starts at 12:15. It is a 60-minute exam, so you have until 1:15. I'm setting up Canvas to give you 5 minutes of grace period. So Canvas won't lock you out until 1:20. But if you're locked out, I'll grade whatever you got submitted. So submit by 1:15. Okay? And if you need to, you can do a second submission and the old one will still be there. But don't wait until 1:19 to submit your midterm. It will be a Canvas quiz. I will give you some suggestions for how to type things, like if you need to write propositional equations, right? I'm going to suggest you use a tilde for not, you use a caret for an and, you use a v for an or, and you use lots of parentheses. So I'll give you some suggestions for writing things like that that are weird. Most of what we have to write we'll just be able to type with plain old ASCII characters as usual. It'll be a Canvas quiz, open book, open notes, no other resources. Okay, so stay away from Google, stay away from other people, and so on. And again, it will go through everything, including number theory, and it stops. The material you're responsible for stops when you started induction. So everything up through, including number theory, GCD, that kind of stuff, modular arithmetic, all of the proofs, all the set theory, functions, all that stuff that we've been doing is fair game. Good source of practice and review. Go through your homework sets, right, and make sure you understand how to do all of those. All right, so let's talk about homework 5. This was the one I just gave back to you. So I graded questions 2A, 2B, 6, 8, 10, and then the questions 1 and 2 that dealt with number theory things. So let's run through those and make sure we're fine with it. So question 2 said, let M of x be the proposition x is a mammal. Let A of x be the proposition A is an animal. W of x says x is warm-blooded. So part A, translate into a formula. Every mammal is warm-blooded. Well, every mammal is warm-blooded, so for all animals, if the animal is a mammal, then it must be warm-blooded, right? So every mammal is warm-blooded would say for all x, if you're a mammal, then you're warm-blooded. All right, so a slightly different expression which is not equivalent would be this. Right? This says for all x, x is a mammal and x is warm-blooded. That's a stronger statement. Okay? That's saying that every creature is a mammal. This statement is saying something much weaker. All it's saying is if you're a mammal, you're warm-blooded. There may not be any mammals in existence. Okay? This requires not only that mammals exist, but in the fact that every single creature is a mammal. Every element of the universe. Okay? So this was what we were after for part A. And then for part E, which most people got translated into English, so this says, x is, for, there exists a creature, right, x, such that x is an animal and x is not a mammal. Okay, so there exists something in the universe which is an animal but not a mammal. For example, a reptile or a fish. All right, let's see. So do we need to know about mathematical induction for the midterm? No, that's the stuff we just started. So that came right after number theory. So everything up through and including number theory is on the midterm, and then starting with mathematical induction, that is not on the midterm. Okay, that will be on the final. All right. Question 4 we talked about last time, and I did not grade that. Question 6 we talked about, but I did grade that. Use quantifiers to say that square root 3 is an irrational number. So a few different ways to do this. If you know about rational numbers, right, this would not be using quantifiers. But, you know, square root of 3 is not contained in the set of rationals. Okay, so that's one way to say that radical 3 is irrational. But to use quantifiers, we could do something like this. For all x contained in Q, x is not equal to the square root of 3. That's a pretty, you know, direct way of saying this. Right, for any element in Q, that element is not the square root of 3. If we didn't want to use the square root symbol, we could do this. For all x in Q, x squared is not equal to 3. So that's fine. If we didn't know about the rationals, or we wanted to just stick with integers, we could say for all x contained in Z, for all y contained in Z, x squared, x over y squared is not equal to 3. And that's sort of one of the most broken down versions of saying this, right? For any integer x, for any integer y, if you take x divided by y and square it, you don't end up with 3. And maybe we need to say something like, you know, z excluding the element 0. So z take away 0. Sometimes z star means z with 0 removed. So it's the punctured number line. But for all cases where x is an integer and y is an integer, this ratio is never the square root of 3. And that's almost the definition of being irrational. All right. Question 8. Use quantifiers to state that for every positive integer, there is a larger positive integer. So let's just translate that pretty directly without a lot of interpretation. Okay? For every positive integer, so for all x contained in, and let me use z plus to mean positive integers. For all x, for every positive integer, there exists a larger positive integer, a positive integer that is larger, a y which is a positive integer such that y is larger than x. So this would be a good translation of that statement. And we can, you know, throw in some parentheses if we want. So for all x, there exists a y such that y is bigger than x. And these didn't have to be positive integers. We could write this statement, you know, across all integers or all reals. And remember, you're not being asked to prove these things. Proving this, really, really hard, right? We're only being asked to state this using propositional logic and quantifiers. And this is actually slightly different. For all x, there exists a y such that y equals x plus 1. And I dinged you a whole point for this. So why is this different from that? Well, a few reasons. Number one, there exists a y such that y equals x plus 1. That is not the same thing as saying there exists a y which is bigger than x, unless you also somehow show that x plus 1 is bigger than x. And that's not a fundamental law of logic, right? And you know, it's obvious x plus 1 is bigger than x. We know that, right? And if we were trying to, you know, use this fact and we needed a y that was bigger than x, we could probably just use x plus 1 and get away with it. But you're actually asked to show that there's a number bigger than x. And if we knew that x plus 1 was bigger than x, then we wouldn't need to do any of this. We could just say, you know, x plus 1 is a number bigger than x. But again, we're not trying to prove this. We're trying to just state what the proposition is using quantifiers. And the proposition is actually, you know, for every positive integer, there is a larger positive integer. That would be this up here, right? That's a larger positive integer. And this needs some work, right? Because you would also need something that states that x plus 1 is bigger than x. So that's a direct mapping of the proposition. And that's pretty subtle, but it's something to think about. All right, so question 10, use quantifiers to say that the equation a plus x equals b has a solution for all values. So what does this mean in common speak? For any value a and for any value b, there is an x such that a plus x equals b. Okay, so for any is another way of saying for all. So let's write this out. For all a contained in R, for all b contained in R, there exists an x contained in R such that a plus x equals b. And you can think of this as propositions, right? And so if you said for all a comma b contained in R, I took off one point, and I gave you some feedback on that. Our universal and existential quantifiers don't work like this. They work on for all some variable, and then some proposition. And it says for any value of this variable, this proposition is true. Or existential, there is a value for this variable which makes this proposition true. But we don't really define these quantifiers with, you know, a set of variables down here. But we can get that effect by doing something like this. But think about it as propositions. This could be the proposition P of a comma b. P of a b is the proposition that there exists an x such that a plus x equals b. All right. So this is also a proposition. For all b, P of a comma b is true. Well, that's a proposition which we could call, say, Q of a. Q of a is the proposition that for all b, P of a b is true. And then our original statement is simply for all a, Q of a. And we could call that some other proposition like M. And we could say, is M true or false? Right? So everything is a proposition, a declarative statement with a true or false value. This is a proposition. It says for all x, it says there exists an x such that ax equals b. Right? It's got a truth value. That's what P of a b is. Different a and b, different proposition. P of 2, 3 is the proposition that there exists an x such that 2 plus x equals 3. Right? And then if we call this thing Q of a is the proposition that for all b this is true. So Q of 5 is the proposition that for all b, P of 5 comma b is true. Which is the proposition that for all b, there exists an x such that 5 plus x is equal to b. I think I said that right. Right? And so you can build it out like that. All right, so that was question 10. Let's go ahead and do the 2 questions on modular exponentiation and Fermat's little theorem. So modular exponentiation, 2 to the 130th mod 7. We're asked to calculate that. So 2 to the 130th mod 7. So write out your exponent as powers of 2. And I happen to know that 128 is a power of 2, and so is 2. So it's 128 plus 2. And now we need to find the modular equivalence of 2 raised to consecutive powers of 2 up to and including 128. So 2 to the first is just 2. 2 squared is 2 squared, which is 4. I'm going to go by squares. 2 to the fourth will be 2 to the squared squared, which is 4 squared, which is 16, and 16 is 2 more than a power of 7. And I got my repeating pattern now. So I'm going to do this without too much work. Alright, and I know 2 squared will be 4, 4 squared will be 2, 2 squared will be 4, this will be 2, this will be 4. Alright, so that's the first step, is write out your power of your number raised to powers of 2. And then, you should be going down the page here, but my page is tilted. 2 to the 130th will be 2 to the 128th plus 2, which will be, now if we pull that exponent down, we switch to multiplication, 2 to the 128th times 2 squared. And that's congruent to 4 times 4, which is congruent to 16, which is congruent to 2. So 2 to the 130th is congruent to 2 mod 7. Okay, that's modular exponentiation. So write your exponent as sums of powers of 2. Find your number raised to all the powers of 2 up to and including the largest one that you need. And do that by squaring, right? Once you know 2 to the 8th, just square it. That'll give you 2 to the 16th. So this jumps up very quickly. If you had an exponent of 1,000,000, it would only take you 20 steps to figure out what 2 to the 1,000,000th is, or 2 to the 20th. Okay, very, very quick to do. And then multiply those out based on which powers of 2 get added to give you your exponent. Every modular exponentiation problem, that's how you do it. Alright, the other trick we looked at for doing large exponents was Fermat's little theorem. So here we did 2 to the 6002 mod 7. And Fermat's little theorem, we want a prime moduli, and FLT says the following. It says 2 to the 6th is congruent to 1 mod 7. In general, it says a to the p minus 1 is congruent to 1 mod p, as long as a is not a multiple of p. So that's the general statement of Fermat's little theorem. For us, since our moduli is 7, FLT says something about 2 to the 6th. And what it says is 2 to the 6th is congruent to 1 mod 7. But 1's a nice number because we can raise 1 to any value and it's always going to be equal to 1. So we can leapfrog over a bunch of exponents and say 2 to the 6,000th equals 2 to the 6th raised to the 1,000th. That's law of exponents. And that's congruent to whatever 2 to the 6th is raised to the 1,000th, which is just 1. And now we just go forward 2 steps to find 2 to the 6,002nd. So 2 to the 6,001 is 2 times 1, which is 2. 2 to the 6,002 will be 2 times 2 to the 6,001, which was 2, so that's equal to 4. Or you can write 6,002 as 6,000 plus 2 and just multiply directly. But that's the basic approach when you're using Fermat's Little theorem to do a large exponent. So use FLT to write your number raised to whatever your moduli is minus 1. And it works best if your moduli is prime. Well, you need your moduli to be prime. It works best when this is not a multiple of P. Alright, so questions on that? The homeworks are looking really good. I think people are getting the key concepts, and the exams will be, mostly like homework sets. So if you're making sense of the homework, you should be able to do pretty well on the exams. Let's see, question: when we are doing quantifier problems, do we only ever have one there exists quantifier? Yeah, you could. You could have a proposition which says there exists an x such that x squared equals 3. And, if you're working over rational numbers, that proposition would be false. If you're working over reals, it would be true. Let's see, do we have to show work? Absolutely, positively, always, right? And I will put a reminder on the exam for things like modular exponentiation. You got to show your work. Which, since we're typing these things in, you may not want to type all of this out explicitly, right? But I need to see something more than just the number 2, right? So at the very least, you're going through all of this. Show me 2 to the 1/30th is 2 to the 1/28th times 2 squared, which is 4 times 4, which is 16, which is 2. Fermat's Little theorem, definitely, right? Show me, that you understand that 2 to the 6 is congruent to 1, and then, you could do something like 2 to the 6,000 is congruent to 1, and 2 to the 6,002 is 2 times 2. Do we have to bold the answer? No, not necessarily. I mean, hopefully your answer is the last part of it, but if there's some confusion about that, like if you follow this with some kind of check, yeah, put your answer in boldface or underline it or something like that, or just put the word answer next to it. My whole goal here is not to be dogmatic. My goal is to make sure that when I'm reading your test, that I can follow your work and I know what you're trying to do. So anything that's going to help me do that, keeping in mind that hopefully I'm being somewhat reasonable about it, right? Anything you can do to help me find your answer and understand how you got there is going to help you if, there's a question of partial credit. Oh yeah, and so implications, which I mentioned for some people, for that earlier question. Implication is just a fancy way of saying if then. So on the question about mammals, right? For all X, if you're a mammal, then you're warm-blooded. This is an implication, right? So P arrow Q, if P, then Q. But an equivalent way to think of that is P implies Q, or Q is implied by P. So that's what an implication is. Alright, are we going to have any questions about proofs? So, I could take a vote, see if people want proofs or not, but I'm not going to do that. Yeah, you'll definitely have proofs. Probably close to half the points may be related to proofs, because that's been a big part of what we've been doing. So it could be proofs about even and odd numbers, or about divisibility, or about whether politicians are honest if it rains on Tuesdays, or things like that. So all the stuff from chapter 3 was proof-related, propositional logic, proving propositions, and you've done bunches of homework questions on that. So you got some good examples of things I might ask. So yeah, definitely proofs, number theory, set theory, a little bit about functions, and whatever else we've been talking about. Who knows? Will there be a study guide, list of things to know? No, we just kind of went through it verbally just now. I don't really have anything more than that. Go over your homework questions. That's a pretty good way to get there. Alright, there's your study guide. So you can go through the list of videos, and we're tagging all of the topics that we talk about. So you can go through that and sort of see a hit list of everything we've been doing. But this will overwhelm you really quickly, right? So I don't recommend doing this. I would say go back through your notes, go back through the homework assignments, and use those as your main guide. And some of this stuff we talked about, like Russell's paradox, I'm not going to ask you about Russell's paradox. I might ask you something about sequences or summations or matrices or injective functions or bijective functions. But the majority of the points are the things that we've been spending most of our time on and that we've been doing most of our homework on. But wow, we've done a lot of stuff, haven't we? We're only halfway through. But we've covered a lot of material already, which is awesome. This course is so many different topics, and they all tie into computer science in one way or another. And some of these topics are, building steps for other topics in the course. But most of the stuff stands on its own, and it's just a really rich course in terms of material. If you come away from here remembering nothing other than the basic idea of a proof and mathematical induction, I'm pretty happy, right? The other stuff will be in there, and it'll tie into other things down the road. But the main themes in here are probably the ones that are coming out from repetition. And when you leave the course, they're probably the things that you'll think back to. What did you cover in 215? I don't know, something about proving something with even numbers and induction, right? That's probably a pretty good takeaway. All right, other questions? I'll pull up my cheat sheet here. All right, let's talk more about induction. So we kind of ended with a postage stamp question. Let's take a look at another postage stamp. Then I want to show you some code. So suppose you have a limitless supply of 3-cent and 7-cent stamps, and you want to do at least 17 cents postage. Alright, so 3 cents, 7 cents, and you want at least 17 cents postage. So P of n be the proposition can make n cents from a combo of 3 cents and 7 cents. That's a horribly worded proposition, but hopefully you know what I mean, right? So P of n is the proposition that we can make n cents postage using some number of 3 cent and 7 cent stamps. Now if we wanted to do this mathematically, what are we actually doing, right? There exist a comma b, both being integers, such that 17 can be written as a times 3 plus b times 7. And then we put it in the set of positive integers, right? That's what we're actually saying, is that we can write 17 as a linear combination of 3 and 7 where those coefficients are integers. Right? But that's too much mathematics. So we'll just think about this as you got a package, you need to put n cents postage on it. Can you do it by putting 3 cent and 7 cent stamps on there without being too short or having excess postage? And since I said, you know, for more than or equal to 17 cents, presumably this is true for 17. That's probably a good base case to check. So P17, is that true? Well, if I do a 7 cent and I do another 7 cent and I do another 3 cent, that's 17 cents. I don't know if people know this symbol or not. It's a symbol for cents. Don't worry about it. So I can find a postage solution that gets me to 17 cents. So P of 17 is true. Okay, so to use induction, we have to prove P of n implies P of n plus 1 for any n bigger than or equal to 17. All right. Well, what was the trick we used on Monday? We took away stamps and replaced stamps and did things like that depending on the situation. So there's one really easy case, which is if you have at least 2 3-cent stamps. So this is going to be case 1. If you have at least 2 3-cent stamps, what can you do? Peel those off, replace them with a 7-cent stamp. So take away 6 cents by peeling off 2 3-cent stamps. Take away 6 and then add 7 by putting down a 7-cent stamp. You've increased the postage by 1. Okay, so the first step here is find some combination of stamps for n cents. In other words, if P of n is true, we know there's a combination that adds up to n, so find that combination. Now, if there's at least 2 3-cent stamps, remove those 2, replace it with a 7. Now our postage adds up to n plus 1. And so we're done. Case 2, there's only 1 or no 3-cent stamps. If there's only 1 3-cent or there's no 3 cents, we can't peel off 2 of them. We got to do something different. Okay. Well, in this case, the 7-cent stamps that are present add up to at least n minus 3. If there's no 3-cent stamps at all, then our 7-cent stamps must add up to n. If there's 1 3-cent stamp, our 7-cent stamps add up to n minus 3. And then adding the 3 cent brings us to n. Well, n is bigger than or equal to 17, so n minus 3 is bigger than or equal to 14. Well, if you have a set of 7-cent stamps that add up to at least 14, how many stamps do you have? At least 2. Our 7-cent stamps add to at least 14. Therefore, you have at least 2 7-cent stamps. These are things that are easy to state. They're not so easy to discover. Okay? I'm stating them, but they're not necessarily obvious. They're not something that starting from nothing, you would immediately come to these conclusions. Okay? That takes some playing around. But they're easy to state, right? If n is at least 17 and there's at most one 3-cent stamp, then n minus all the 3-cent stamps is at least 14, which means you have at least 2 7-cent stamps. Alright, if you have at least 2 7 cents, remove 2 7 cents. That takes down 14 cents of postage. Replace that with 5 3-cent stamps. That adds 15 cents. Your postage has gone up by 1. So take off 2 7s, add 5 3s, and now your total postage is n plus 1. And so in any of our possible cases, which is either you have at least 2 stamps worth 3 cents, or you have fewer than 2, P of n implies P of n plus 1. So our inductive step has been proven, and together with our base case, we can conclude P of n for all n bigger than or equal to 17. Alright, so that's a weirdish proof, right? Here's some code. Now remember, in C, when we try to pass variables to a function so that we can change them, we have to get into all this pointer nonsense, right? And asterisks and things like that. Don't want to get bogged down on that, okay? That's not the punchline here. But let's just take a look at this from kind of a higher level or a pseudocode level. And, you know, also see there's all this weirdness of doing fgets and scanf and stuff like that. I don't want to get bogged down in that either. Okay, so a really sort of cursory pass through this code. What's going on? I'm going to ask you how much postage you want. I'm going to get that postage into something called total. And if you ask for less than 17 cents postage, I'm not going to do it. I'm just going to say try again. Otherwise, I'm going to call this solve function. And solve takes 3 arguments. The amount of postage I want, and then 2 placeholders. And it will return to me the number of 3-cent and 7-cent stamps to add up to that total. And then I'm just going to print them out. Number of 3-cent stamps is 3, number of 7-cent stamps is 7. So this is just a main program to exercise this solve function, which takes total postage, gives you back the number of 3s and 7s. Alright, so what do we have to do to write solve? We're just going to mimic the inductive proof that we just did. If your total is less than or equal to 17, that's our base case. We're going to say do 1 3-cent stamp, do 2 7-cent stamps. So we're going to give you 17 cents postage. Alright, that's the base case. If you want 17 cents or less, we'll do 1 3-cent and we'll do 2 7 cents. Otherwise, a pair of possibilities. So first, we're trying to solve this for a postage of total. We're going to assume that we can solve it for n minus 1, right? We're going to solve it for total minus 1. So we're going to solve that, and we're going to find out how many 3-cent and 7-cent stamps give us 1 penny less than what we want. And then we're going to look at our 2 cases. If you have at least 2 3-cent stamps, we're going to take away 2 of those, and we're going to add 1 7-cent stamp. Again, don't get bogged down with the asterisks and all of that stuff. This is ignoring the C weird syntax. This is a direct translation of what we were doing. What we were doing here, right? If you have at least 2 3-cent stamps, we're going to remove those 2 and add a 7. So at least 2 3-cent stamps, take off 2 of the 3s, replace it with a 7. Otherwise, if you don't have at least 2 3-cent stamps, you know you have at least 2 7s, take off the 2 7s, replace it with 5 3s. So take off 2 7s, add 5 3s. And that's our whole solve function. And there's nothing in this function that really kind of addresses the larger scale question of how do I get this postage out of 3s and 7s. All we've done is really code up the inductive proof that we can find a solution. And this function only does two things. One, if you ask for 17 cents postage, it gives you an explicit solution. Otherwise, it solves a solution for 1 penny less, and then changes that into the solution for our desired total. So if we run that, enter our desired postage, well, 17 is just going to give us a 3 and 2 7s. 18 will give us 6 3s. 19 will give us 4 3s and a 7. 20 will give us 2 of each. 21 will just use 7s. 2,323 will give us 331 7-cent stamps and 2 3-cent stamps. And so on. Alright, so what's going on here? Well, we have an inductive proof that you can do this, that you can write some number bigger than or equal to 17 as the sums of 3s and 7s. We've taken that proof and used it to cobble together a function to give you a solution by mimicking the steps of that proof. But there's another thing going on here. Suppose somebody hires you to write a solve function which will solve this postage stamp question, and you present them with this code, and they say, how do I know this code works? You ran it for a few cases and it worked for those, but how do I know that this code works in general? So how do we prove that this code actually works? There's a 2-word answer. Anybody want to venture a 2-word answer for how to prove that the solve function is correct? Mathematical induction, perfect. So let P of n be the proposition solve of n works correctly. You pass 2 other arguments to it, but basically using my solver for n, P of n is the proposition that solve works correctly for the value n. And we've told the person, you know, this code only works for n bigger than or equal to 17. So our goal, in order to get our paycheck, is say prove P of n for all n bigger than or equal to 17. Well, how are we going to prove the correctness of this code? Using mathematical induction. 2 steps. First, we're going to prove a base case. Prove P of 17. What is P of 17? It's the proposition that our solve function works correctly if you pass it the argument 17. Well, how do we prove that? It's pretty straightforward. If you call this with an argument of 17, you can see this if statement is going to be true. It's going to set 3 equal to 1. It's going to set 7 equal to 2. Is that a solution? Yeah, because 2 7s is 14, plus a 3 is 17. Yeah, my function works great for 17. So by looking at the code, we can verify that P of 17 is true, i.e. my solve function works correctly for 17. Okay, inductive step, prove that P of n implies P of n plus 1, where n is bigger than or equal to 17. i.e. prove that if my function works for n, it also works for n plus 1. And that's as straightforward. So I want to prove that my function works for total, and there's an equivalent form, which is prove p of n minus 1 implies p of n, where n minus 1 is bigger than or equal to 17. So n is bigger than or equal to 18. But don't worry about the edge case, right? So we have to prove that if my function works for n, it also works for n plus 1. Well, if I pass in some value of n plus 1 here for total, right, and that number, suppose it's bigger than 17, so this if statement never fires. Well, first thing it's going to do is it's going to call the same function for total. Well, you know, if total is n plus 1, then calling this for total minus 1, that's calling it for n. And our inductive hypothesis is that p of n is true. Our solve function works for n. So if I'm trying to prove that my solve works for n plus 1, first thing that my code's going to do is call the solve function for n. We know that's going to give us a correct answer. That's our inductive hypothesis. So this is the number of 3 and 7 cent stamps to add up to total minus 1. And now we just go through the code and the two possibilities. If the number of 3s is bigger than or equal to 2, when we subtract 2 times the number of 3s and we add 1 to the number of 7s, that total will be the original total, which was total minus 1, plus 1. And if that was not the case, then we know that this number of 7s is at least 2, so subtracting 2 leaves it as non-negative. And adding 5 to the number of 3s gives us an integer number of 3s. And this will subtract 14, and this will add 15, so the sum we get when we add these together will be the sum we got up here, plus 1. Well, the sum of the 3s and 7s from here was total minus 1. When we add 1, we'll get total. And so whichever section of code fires, when solve returns, total will be equal to the number of 3s times 3 plus the number of 7s times 7. And so it's pretty easy to go through the code and see that if it works for n, then it also works for n plus 1. And therefore, with mathematical induction, p of n is true for all n greater than or equal to 17, i.e., our solve function works for all n bigger than or equal to 17. And that's it. There's your full rigorous proof. Yeah, I can post this code somewhere. I'll post it in the 224 code area. There's a few people in here who aren't in 224. Actually, I'll tell you what, I'll post it on the Linux server, because everybody here has Linux server access. So I'll put it under /temp/stamp. And I'll also put it in the 224 area that you can get to from Canvas. I'm making myself a note. All right, cool. Questions about that? That may and probably should seem a little bizarre at this point, okay? But it's you know, a connection between this kind of abstract propositional logic stuff and some extremely concrete question of validity of algorithms. All right, let's see. What else should we try? let's look at subsets. So cardinality of power sets, the number of subsets of a given set. So remember, we have this idea that nope, I didn't close it. Alright, hold on a sec. Yeah, I lost my document camera. Okay, hold on. Let me reset my cameras. Alright. So we have this idea. If you have a set with, say, 3 elements in it, we define the power set to be the collection of all subsets. And it turned out that if we had 3 elements in S, we had 2 to the third or 8 elements in the power set. And if you had 5 elements in S, you would have 2 to the 5th or 32 elements in the power set. And I suggested that there was a general property, which was the number of elements in the power set of S was equal to 2 raised to the number of elements in S, as long as this is a finite set. And the power set is just the collection of all subsets. So this is really just the number of subsets of S is just 2 raised to the power of S, the cardinality of S. And when we talked about representing sets in binary, we had this idea that if we ordered the elements of the set, which we don't do in a pure set, but if we assigned an ordering on top of the set, we could write a binary number where each bit of that binary number corresponded to a 1 or a 0 to indicate whether the corresponding element was in the set. And so this would correspond to the empty set. 1, 0, 1 would correspond to the set AC. 0, 1, 1 would correspond to the set BC. All 1s would correspond to the set ABC, and so on. And there was a 1-to-1 mapping between these 3-bit numbers and possible subsets of ABC, which means the total number of subsets was just the total number of possible 3-bit numbers. And from Engineering 250 and other courses, we know that the number of 3-bit numbers is just 2 to the third. And so that was one way to see that this property holds for the number of subsets of a finite set. But let's prove this using mathematical induction. So let P of n be the proposition a set with n elements has 2 to the n subsets. Alright, that's what our proposition P of n is, and we want to prove P of n for all n bigger than or equal to 0. Now a set always has an integer number of elements, and since we're only dealing with finite sets, right, the number of elements n is always an integer, and it's obviously bigger than or equal to 0. could be 0 for the empty set. All right. So this is our statement of our quest in terms of propositions. P of n is the proposition that a set with n elements has 2 to the n subsets. And we want to prove P of n for all n bigger than or equal to 0. We're going to use mathematical induction. So step 1 we're going to do with our base case. We're going to prove P of 0. Well, P of 0 says a set with 0 elements has 2 to the n subsets. So if P of 0 says the empty set has 2 to the 0, 1 subset. So P of 0 says the empty set has exactly 1 subset. And in fact it does, right? It has a subset which is itself. And it can't have any other subsets, because if X is a subset, then every element in X must be in the empty set. Since there's no elements in the empty set, there can't be any elements in X. So you can actually prove with a bit of work that it not only has a subset, but it has exactly 1 subset. But we've already talked about this, right? So P of 0 is true. So the more interesting part is usually the inductive step. Prove that P of n implies P of n plus 1, where n is bigger than or equal to 0. And again, doing this strictly formally would take a fair amount of writing and definitions, and would probably obscure the inductive part, which is what I'm after here. So I'm going to go a little hand wavy with some of this, okay? But here's the basic idea. So let S be a set with n elements. Okay. Let T be a subset of S. I'm not going to do that. Let me do something else first. Let S be a set with n plus 1 elements. All right. So I want to prove that this has 2 to the n plus 1 subsets. Okay, so I'll write that down. Let's prove S has 2 to the n plus 1 subsets. If we can do that, we've just proven P of n plus 1. Right? We've proven that a set with n plus 1 elements has 2 to the n plus 1 subsets. Okay? We're given P of n. That's our inductive hypothesis. So we're given P of n, we're trying to prove P of n plus 1, which is that a set S with n plus 1 elements has 2 to the n plus 1 subsets. Okay, so I'm just going to concentrate on this goal. Alright, remember I made mention last week of something called the axiom of choice? We're going to use the axiom of choice. So let X be an element of S. Okay, can't prove that you can actually do this, but if we assume the axiom of choice, then we're allowed to say let X be an element of S. Okay, so if I take away that element from S, this has this has n elements, right? And since we know P of n is true, right? That's what we've been given. So this set S minus X has 2 to the n subsets. All right. So let T be a subset of S. Any subset. So S is our set with n plus 1 elements. Pick any subset of that. There's 2 possibilities. possibility 1, X belongs to that subset. Possibility 2, X does not belong to that subset. Alright, here's the intuition. If X does not belong to the subset T, right, then X is actually a subset of this. Or, sorry, T is a subset of this. So if T does not contain X, T is a subset of this. Right? We know T is a subset of S. But if X is not contained in here, then T is actually a subset of S minus X. Alright, so how many possible subsets are there of S that don't contain X? Exactly the number of subsets that there are of S minus X. Alright, so if X is not in T, T is a subset of S minus X. And so the number of such subsets is 2 to the n. Why? Because P of n. Alright, the other possibility is that our subset of S does contain X. Well, in that case, T is just T minus X unioned with the singleton set X. And T minus X is a subset of S minus X. Right? Same thing as over there. So how many different subsets are there of T minus X? Again, there's 2 to the n. And for each of those 2 to the n, if we union X, we get one of these subsets that does contain X. Alright, so let's strip away all the mathematics and let's just look at this intuitively. We're looking for subsets of S. If our subset does not contain X, it's a subset of this smaller set containing only n elements, and we know there's 2 to the n subsets. If our subset of S does contain X, we have a subset of our smaller set plus X tossed into the mix, and there's 2 to the n of those. And any subset either contains X or doesn't contain X, and so the total number of subsets is 2 to the n plus 2 to the n, which is 2 to the n plus 1. Okay, that may take some head scratching, but it's the basic inductive approach, and if we were to try to do this with what we just did, there's our original set S. The power set of S contained the following: A, B, C, AB, AC, BC, the original set, and the empty set. Okay, those are all the subsets of a set with 3 elements. Suppose I have a new set, let me call it S2, where I add a new element D, and I want to list all the subsets of that. I don't have to do any work. These are all subsets. Right? My new set contains ABC, so I want to list all the subsets of this new set. Well, all the sets that I listed as subsets of ABC, those are certainly subsets of this. But none of those contain the letter D. If I take each of those and I add the letter D, I get another collection of subsets. And that's the whole set of subsets. Right? Either subsets of that or subsets of that plus the letter D. And if I know that I had 8 here, then I've also got 8 here, And so the number of subsets of this will be 8 plus 8 is 16. That's the intuition of everything we just did. So knowing that this property holds, knowing that holds for n elements, it's easy to argue that it holds for n plus 1 elements. And combined with the base case, which is that the empty set has one subset, we can prove that this is true for a set containing n elements where n is any integer bigger than or equal to 0. Alright, again, the goal here is mathematical induction. This is just an example of using mathematical induction in a way that has nothing to do with adding integers or tiling floors. Alright, let's see. So questions? Prove that n is less than or equal to 2 to the n for all n bigger than or equal to 2. So let P of n be the proposition n is less than 2 to the n. P of 2 says 2 is less than 2 squared, which is 4. That's certainly true. So given P of n, we know n is less than 2 to the n. And so n plus 1 is less than 2 to the n plus 1. And we know that n is bigger than or equal to 2. So n plus 1 is less than or equal to 2 to the n. And if n is bigger than or equal to 2, then 2 to the n is bigger than or equal to 4, which is certainly bigger than 1, so 1 is less than 2 to the n. So n plus 1 is less than 2 to the n plus 1, which is certainly less than 2 to the n plus 2 to the n, which is 2 to the n plus 1. And so with a little bit of arithmetic, we've proven n plus 1 is less than 2 to the n plus 1. Well, that's what P of n plus 1 says. Therefore, P of n implies P of n plus 1. Therefore, by mathematical induction, P of n for all n bigger than or equal to 2. And we're done. All right? This is just a big stick you can take out and whack at all kinds of things. And once you get really good at wielding it, right, to write this formally for a really picky teacher would take, more words and such. But to form the argument in your head that, you can use mathematical induction to prove this, and more importantly, to convince yourself that this is true, whether it's, a piece of code you're writing or something like that, you pull out your mathematical induction stick and you just, go to town on it and things just crumble in front of it. It's a really, really powerful tool. How is 2 to the n bigger than or equal to 4? Because n is bigger than or equal to 2. And so 2 to the n is bigger than or equal to 2 to the 2, which is 4. You do need to know that, 2 to the 3 is bigger than 2 to the 2. So, like I say, you'd need to do some formalism in here to do this. Right, so that needs to be shown depending on what you're given and what you're asked to actually show. But in terms of trying to see, for yourself that this is absolutely true, where we would assume that you believe that already, right, this jumps out immediately. And this comes up when you want to do things like, show for a big enough n factorial is less than n to the n. For sufficiently large n, and that's smaller than 2 to the n, and that's bigger than n squared. And those come into play when we talk about order of complexity. When we look at algorithms and we ask how much time does it take to solve a particular algorithm, and is this algorithm better than that algorithm? Well, we don't talk about how long an algorithm takes because that depends on the program, how it's written, it depends on what hardware you're running it on, and things like that. But what we are interested in computation often is how does this solution compare to that solution in terms of, as the problem grows, how does the performance change? And we'll talk about this possibly at the end of this course, but definitely in the CS222 probably. Something that grows as n factorial is worse than something that grows as 2 to the n. And that's way worse than something that grows as n squared. If n gets big enough, right, if n is equal to 10, this is 100, this is 1,000, this is, something with a bunch of zeros, this is 10 to the 10th with even more zeros. And we can run that kind of analysis using a simple inductive proof like this. All right, so midterm, Friday at 12:15. We'll spend the first 15 minutes letting people come into the room. If you have questions or things you want to go over, we can do that. Exam will run until 1:20, and then we'll have a half hour left, which we'll spend just sort of doing some fun stuff, or talking about the midterm if you want. But I'll show you the square root of 2 is irrational. We'll probably talk about odd pi fights and the colors of horses. All right, and I got office hours at 5 to 7, so come by there if you have questions or things you want to go over. Thank you, everybody. Have a good one. See you next time.